Welcome, everyone. Today, we are having Professor Filiz Garip from Cornell University. And I should say that I met Filiz Garip for the first time in 2006 on the day that she was given her mock job talk, finishing her PhD and preparing for the mock job talks. And that was my first mock job talk practice exposure in sociology at all. And I was very much in the self-doubt of whether what sociology field is about at that stage, and recently finished my econ masters. And Filiz has given such an impressive talk about networks and migration at that stage, finishing the PhD and setting a very high standards about like what a good sociological talk, quantitatively rigorous, could be. That just changed the entire view of my discipline and then my excitement about sociology fields, I should say. And since then, we have watched her impressive career trajectory, and she moved to Harvard and became a professor of migration and sociology in Harvard, and then moved to Cornell University now as a professor of sociology at Cornell. So without further ado, I just leave the space to Filiz to talk about her recent paper on how combination of and sequence of weather events shape Mexico and U.S. migration flows. So floor is yours, Filiz. Thank you so much for being here.
Well, thank you so much for inviting me. I don't even remember that, Berkay, so thanks for taking us back to that time. So I have many collaborators on this project, and I don't think I would have gotten into the topic had I not moved to Cornell. So here I moved, when I moved, I met a lot of people from economics and from the natural resources department here who were working on the impact of climate change on human behaviors. And I started collaborating with them. We got 2 big grants from Cornell. Actually, migration is Cornell's stated grant challenge that it wants to address in the next couple of years. So they've been very, very supportive. We were also very lucky to recruit amazing PhD students to our group. And today, the first part of the talk is about a project that Mario Molina is leading, and he just finished his PhD and starting a postdoc at NYU Abu Dhabi. And Julia Zhu is actually leading the second part of the talk, and she is on the economics track in the policy analysis and management department here. So let's see. Okay, so basically there's growing interest in how environmental events shape migration decisions. And as a migration scholar myself, to this date, I've considered social networks, economic factors, political factors as a potential driver of migration, but I've completely neglected environment. But the context of climate change is actually making all of us pay more attention to how weather fluctuations or sudden onset events can impact human mobility. And we want to understand these patterns, especially to be able to predict human displacement in the future as a result of these factors. So when you look at research in this area, it's a fast-growing line of work, and studies mostly focus on weather fluctuations measured through temperature and precipitation. So you look at historical data and you try to gauge how differences from some baseline impact mobility now. There's also another line of work that looks at sudden onset events like storms or other disasters and how they displace people. But for this talk, we're only focusing on gradual weather changes measured through temperature and precipitation. And when you look at the literature, some of the findings are quite well established. For example, Kaiwan Munshi, who's an economist, wrote one of the first papers in the context of Mexico-U.S. migration, and he established low rainfall in Mexican communities to be related to more U.S.-bound migration. So he didn't test the mechanism, but the suggested mechanism was agricultural production. So if it doesn't rain, your production goes down, you're economically constrained, and then you migrate to cope with that. So later work directly tested some of these mechanisms, the link from weather to crop yields to migration. So the Feng and colleagues study appeared in PNAS. It was later challenged because of its empirical specification was not as stringent as it should be. But this finding that low rainfall leads to lowering of crop yields and more migration is pretty much well established and actually makes sense. But there are some other findings that are more mixed and hard to interpret. For example, a recent work by Fernando Riesmena and his colleagues, again, looked at Mexico and connected low rainfall to more migration, but this pattern held only in well-off communities, so communities with some economic resources. So the idea was such communities could finance the mobility of people. And again, it makes sense. But then they also looked at temperature, and they found the opposite pattern. So high temperature, which is again related to drought and lowering of crop yields. They found that this led to more U.S. migration, but only in poor communities. So basically, this is one example that I picked, but it's emblematic of how the results can vary across different measures, across different settings, across different kinds of models that are being tested. And part of the problem is we have no theoretical guidance on how to specify the link between weather and human behavior. And it's hard to come up with the correct specification. And there are other issues that we need to deal with. First of all, communities have different normals, and we need to correct for that. For example, extremely hot weather in a place that is always hot may not be so dramatic, but the same weather, extreme hot weather in a typically cool place, will have a huge impact on people's economic fortunes. But studies go about correcting for this place-specific normal in different ways. So some studies argue that we need to look at the long normal, let's say between 1960 and 1990, and compare everything after that to that 30-year baseline. Other studies argue that that's too long of a period. We should look at the last decade. And that obviously changes the results. And then, we don't know when the response to weather actually occurs. Is it immediate? Is it in 2 years, 1 year? So we might have this delayed response, and studies use different lags to correct for that. We also don't know if we should measure this annually, monthly, daily, so on and so forth. Weather fluctuations are also difficult because they might create a cumulative response. For example, let's say that you have low rainfall in a rural community, but there's an irrigation system. So you don't see an impact in the immediate aftermath of this. But then if there's another year of low rainfall and the irrigation has run out, then you might suddenly see this effect. So you might see this intensification of effects. Or you might observe the opposite, right? You might have a decaying response to weather fluctuations because a community has adapted to the new normal. So basically, there are many ways of specifying the link between weather and migration. And you might consider complex interactions between contemporary weather and past weather at various lags to take into account adaptation and intensification. And you might also consider, like Rios Mena and colleagues, that the interactions between weather and other social and economic factors at the household level or at the community level. So you might want to look at heterogeneity. And again, it's very hard to consider all of these complex interactions. So if you consider, let's say you have 50 variables in total, if you consider all possible interactions, you suddenly end up with more parameters than observations. And we might end up with a model that's too complex. And even if we were able to estimate such a model, we might overfit the data at hand. In other words, we'll capture the noise as well as the signal in the data. So this is not something that we typically consider in the social sciences because we have a strong preference for simple, well-specified models that we estimate with some version of an OLS. And obviously, this is an advantage of kind of positing a structural model for the data at hand. It allows us to look at the relationships between an input and an output, but we're also imposing this linear, mostly linear view on the world. So we want to kind of relax that. And we want to relax that, especially in the context of weather, because we don't have any theoretical guidance on how things should work. And we want the data to help us decide which of these interactions are actually most meaningful in explaining the patterns in the data. So for that, we turn to machine learning tools. And these tools actually allow us to estimate really, really complex models without overfitting the data. That's their premise. So basically, machine learning, as many of you might know, it's a field at the intersection of statistics and computer science, and the goal is to automate discovery from data. And in the old times, intelligence systems basically coded all possible outputs for all inputs that you have. So you basically hard-coded these rules. But nowadays, intelligence systems are estimating complex functions to learn from data. So Mario and I actually wrote a review article on this in the Annual Reviews of Sociology on applications of machine learning for sociology, drawing on social sciences more generally. And there we talk about two general classes of machine learning tools. So one is unsupervised machine learning, where you're only considering an input, let's say a bunch of variables that you have, and you're trying to come up with a representation, a simpler representation of that data. For example, cluster analysis might help you find different groups in the data. And I've done some of this in my earlier work. But here we're focusing on a different class, which is known as supervised machine learning. And here the goal is to take an input or independent variables, as we would call them in social sciences, and link it to an output Y. And your goal is not only to fit the data at hand, but to basically train a model that would give you good predictions on previously unseen data. Now, again, maybe some of this is redundant, but in the social sciences, we're very used to using OLS, where you basically come up with a distribution that could have generated your data, you propose a simple model, and then you estimate parameters of that model using the data, and then you interpret these parameters as the mechanisms linking X to Y. But we often ignore model uncertainty. We take one model and then we basically look at the fit or evaluate the fit with the same data. So we ignore out of sample performance of our model. In the supervised machine learning, basically we consider very complex, often non-parametric models, and your goal is to have predictive accuracy on new data. But most of the time, these tools give you black box results. In other words, you have a model that can predict, but you don't exactly know why it predicts, and you don't gain much of an insight on the links between X and Y. Now, here, the SML, the downside of SML is worth, compromising on, because we want to ask a simple question. Can we predict migration at the individual level, first of all? And can we predict it better when we consider weather? And can we use these, complex models to tell us which variables are most predictive of the weather migration relationship? So these are some of the things that we're doing. And by the way, this is ongoing work. So I'll present some results, but this is not all said and done. So the method that we begin with is based on the so-called regression trees. So here you're considering a tree-like model that splits into branches in the input space X. And then at the end of each branch, you have a prediction for the output that you're interested in. And it's very good at capturing nonlinearities and interactions in X. For example, let's say that we want to predict a binary migration outcome with two indicators, age and education. So we can imagine the tree first splitting with respect to age. So you split your data into young and old. And then each of these branches further splits by education into college and no college. And then at the end of each of these branches, or the node, it's called a leaf, you have a prediction. So in this case, young and college-educated people are migrating, the others are not. So you can imagine that with enough splits, you can perfectly fit the data at hand. But the goal is to have predictive accuracy outside your own data. So you put some constraints on the setup to make sure that you're explaining the data at hand, but also your model is generalizing to other data sets. Now, we use a version of this which estimates not a single tree, but thousands of trees, and then averages over them. So these are called random forests. And these are good at giving accurate predictions, but then because it's averaging over multiple trees, it's basically harder to interpret the relationships. You can still get some understanding of which variables are more important in the predictions, but other than that, you don't necessarily get the kinds of OLS estimates that we're used to. So the data comes from the Mexican Migration Project. And this data set, the collection started in the 1980s, and it's still ongoing. So in every year, researchers have gone and picked 3 or 4 Mexican communities, and they've randomly selected 200 households in those communities. And they collected information on everyone in those households, retrospective life histories. So let's say you were a migrant in a household, you were not there when we were collecting data, then we would ask your mom or your spouse about you. So that's kind of how the data works, and the response rates have been always over 95%. So right now we have information on about 140,000 individuals, and about 20,000 of them have migrated to the US at least once. And the data come from 170 communities, and they have pretty good geographic coverage. I think they cover 21 out of 24 states in Mexico. And then the observations are between 1980 and 2019. Again, this is not panel data per se. You know, every community is surveyed once, but because of retrospective life histories, we know every year of a person's life, what they were doing. We can construct this panel structure. So we take these communities and then we overlay on them daily weather data, which is at a very fine resolution. So basically, this is daily data that covers every 1 kilometer square grid on Earth. And we basically take the community shapefiles and then we average over the grids to come up with these measures. And this is something that we learned really early on. A lot of the work in the literature was using data at a lower resolution. So a lot of the studies that I mentioned, like Munchi's study or Rios Mena's study, are at the state level. So the weather is measured within a Mexican state, or at best at the municipality level. And we wanted to see if this would make a difference. And here we're showing a simple graphic. So we're basically here looking at precipitation in Mexican states in year 2000. And we're basically normalizing each state level measure by its own normal in the period from 1980 to 1984. So basically, we're looking at the difference between the two, and then we're measuring that difference in terms of standard deviations. Basically, in year 2000, how many standard deviations off were you in terms of the annual rain that you got? Now, basically, pale colors closer to white means there hasn't been much change. If it's red, it means your state received less than its baseline in 1980s. And here, if we look at the state level data, we see that most states are either white or pale pink. So either experience no change or experience a little less rain than they did in the 1980s. But then if you look at it at the municipality level, on the right-hand side, you see a lot more variation within a state. For example, I pulled out one state. This is the state of Sonora in the green rectangle. And here we see it's white. It's as if nothing has changed. But when we look at it at the municipality level, we see a lot of communities, little municipalities that are blue, which means they received more rain than their baseline, and a lot of communities that are kind of darker shades of pink. So basically, looking at things at a finer resolution makes a lot of difference. And in our case, communities are tiny. Imagine like one dot in the municipalities. And because there are these microclimates, it really makes a huge difference if we use state level, municipality level, or community level data. So this is kind of one thing that we've learned. And the same thing with temperature. This is the same graphic looking at the temperature at the state level versus at the municipality level. So basically, the output that we want to understand or predict is the first migration trip to the United States. We're not looking at repeated trips because, you know, as you make more trips, your characteristics change as a result of migration. So we want to stay clear of that reciprocal relationship and looking at just the first trip. And we consider a bunch of different inputs, you know, that are, you know, typical in the migration literature, like your age, sex, education, your household wealth, your prior migration experience. We actually, you know, estimated, you know, alternative combination of these variables, like excluding everything that could be endogenous to past weather, but, you know, doesn't make a difference. And then community involvement in agriculture, rural, urban status, so on and so forth. Now, the really exciting part is when it comes to weather, because typically you need to hand select a few variables and you're worried about multicollinearity, all of these things. And because that's why kind of it's been hard for results to accumulate in this area of research, people use slightly different measures. So, and then it makes it hard to compare results across studies. So here, because we're using these machine learning tools, and these tools really shine when you have more parameters than observations almost. We basically include everything that we could think of. We looked at the literature And we included every measure that we could see in past studies. We also included many, many lags, not just 1 or 2 lags, but 5-year lags for each measure. So we want our data to tell us if any of these measures are better than the others. Now, one point to make here is that when we fit a typical OLS model, our goal is clear. We want to get the best in sample fit. So we use the same data in selecting the model and in also assessing its performance. But then in SML, the goal is to predict out of sample. So you want to gauge that. So you typically separate your data into 3 components. You have the training data to fit different models. You have the validation data that helps you select the best one among them. And then there's a test data set that you keep in the vault and you don't touch until you're done, until you know what your best model is, and you use that to assess the performance of the final model. So we haven't touched that data yet. And of the 140,000 individuals in the data, we set aside 50% of them to the training data, and the remaining 50% go, like half of it goes to validation data and half of it goes to test data. Again, we haven't used the test data. Now, can we predict migration is the first question. Yes, and too well, but that's not a good thing because there's a big imbalance in the data. So one of the biggest decisions we had to make was how to structure the data. Remember, we have multiple observations from the same individual over time. So our first attempt was to look at it in terms of, person years, like we would do in a typical regression. What if we included, let's say, 50 observations from each person because we have data over time, but then that makes our data really unbalanced. So we end up with 2 million person years and only 20,000 migration events, so less than 1% of the observations. So if we have a model that always predicts no migration, it's really, really accurate 99% of the time. Well, if we we factor this in, the answer to this question changes, and we see that we don't predict that well. Well, we do well in the training data. So here we're comparing the predictions for non-migrants and migrants. Basically, the share of or the percentage of times our model correctly predicted the class a person belonged to. And this is again in the training data. We see that for non-migrants, we have 100% accuracy. For migrants, 87%. So we can live with that. But then when we look at the validation data, the results are horrible. For non-migrants, we can, again, predict 99% of the time. But for migrants, we can predict only 6% of migration trips. So this means that we're overfitting our data, our training data. So we need to do something about this. This is why the validation data is helpful, because you can go back to the training data and fix certain things about your model. So basically, in order to avoid overfitting, we put some constraints on how deep our trees can go. We also played with the relative cost of making a mistake in predicting migrants versus non-migrants. So we basically increased the cost of making a mistake for migrants. And when we do that, our basically predictions get a little bit better for the migrants. So here we're making the cost of making a mistake in migrants 1 million times higher than the cost of making a mistake for non-migrants. And we see that our prediction accuracy moves from 6% to 53% in the validation data. And this comes at a cost of reduced accuracy for non-migrants. So it went from 99% to 92%, but you can see the trade-offs here. And then if we further increase the cost to 10 million to 1, we see that this now, we really are doing a poor job in predicting non-migrants and doing an excellent job in predicting migrants. Now, one solution we found to this is obviously playing with the parameters of the model. Another solution we found was instead of using person years, create a wide data format. So basically each individual will be included once, but the entire history of that individual would be included as different columns. And that, we're not done with those results yet, but that seems to be a better strategy here. Now, basically, if we go back to the original question, can we predict migration better with weather indicators? In other words, how much of a difference does weather make in our predictions in a given model? Now, this is a so-called ROC curve. I think it stands for receiver operating characteristic, not a very descriptive name, but basically it's a performance evaluation graphic. So basically you're comparing the true positive rate on the y-axis to false positive rate. So if you have a perfect model, your true positive rate would go up to 1, and then it would be straight at 1. And you look at the area under this curve. So the larger the area under the curve, the better performing is your model. So area under the curve is at a maximum can be 1. This means that you can separate your two cases, migrants and non-migrants in my case, perfectly. Now we see that none of our models here represented by a curve are quite there yet. And different colors here represent different models. And the red color is the model with no weather data. And then the other models include different combination of weather indicators. So we see that we do slightly better when we include weather, but not by a whole lot. We see that area under the curve is about 0.79 when we don't have weather data. And when we include the weather data, it improves to 0.80 to 81. So this means that we can predict the outcome with an accuracy of 80 to 81%. So a slight improvement, but not a whole lot. Now, the second question we can ask is, does this do better than a simple OLS with hand-selected indicators? Let's see, we kind of selected the most popular indicators in the literature and fit a logistic regression to the same data. And again, SML does a little bit better, but not by a whole lot. And the area under the curve with the logistic regression is, I think, 0.78. So, not a huge difference. And this result is actually in line with recent findings from social sciences. For example, Matt Salganik and his hundreds of collaborators published the results from their mass collaboration effort. And here, this was a competition set up at Princeton University, and Princeton University actually houses the fragile families data. And this is a panel data set that started in 2000 and has been following the same families over the past 20 years. And there are about 4,000 families here. So the goal in this competition was to train models to predict 6 life outcomes, like your GPA or your likelihood of dropping out of high school, using the existing data. And then the results would be evaluated in the unseen data, the new wave of data collection. So 160 teams participated in this effort, and they used all kinds of machine learning tools, and they competed against each other. And the results were actually quite striking, but not in the way that we expect. And basically, whatever model you used, the predictions were not good. And actually, a simple model with expert chosen indicators, like 5 or 6 indicators, did almost as well as the most complex ML method. So I was asked to write a commentary on this. And in the commentary, I said a bunch of things which I think apply to our study with Mario as well. Basically, what does it mean that we're not able to predict these outcomes, whether it's kind of educational outcomes or, migration behavior? Basically, one suggestion is maybe our data, the survey data, are missing key aspects of people's lives. So we're used to asking about SES, like all these kind of fixed indicators that we replicate across surveys, but maybe we're missing certain things that are really, really crucial. Or it might be that life outcomes are too idiosyncratic. Individuals are too hard to predict anyway, and there's a ceiling to predicting things at the individual level. This doesn't mean that as social scientists, we don't understand aggregate relationships between, let's say, education and income, or your household wealth and your migration likelihood, but this is not enough to predict it at the individual level at this kind of fine resolution. So these are all kind of on the downside. But on the upside, what we're learning is our existing parametric, simple linear models are actually not that bad. They can perform quite well, especially when combined with domain knowledge. So in the second part of the paper, we're moving in that direction. And now that we know these predictive models are not gaining us a whole lot in terms of predictive accuracy, can we go back to the drawing board and can we use our domain knowledge to solve some of the problems I identified that we don't know which indicators are the best? Can we use this domain knowledge to pick the things that should matter in linking weather to migration? And this is joint with Julia, as well as Nancy and Amanda. So basically, to do that, we start from our qualitative data. And in 2019, we did field work in Mexico, and we went to the mountains of Chiapas, where there's coffee production. And coffee is actually one of these things that is most affected by climate change. So we wanted to see how farmers were thinking about this. We also talked to corn growers in Jalisco. And Jalisco is in central western Mexico. It's one of the highest migration prevalence states in Mexico in terms of US bound migration. So we wanted to see if changes to farming, changes to weather had something to do with that. And we wanted to gain some insight into what the relationships might look like so that we could test them with our survey data. So here's what we learned from fieldwork. First of all, this is not very surprising. Weather is a lot more unpredictable now, and farmers recognize that. So for example, a corn farmer in Jalisco talked about how they knew how much it would rain. And as a result of that, how, high the lake would go, flooding areas around it. But nowadays, it's really hard to predict that. So they can lose their investments really quickly. And similarly, a coffee farmer in Chiapas said the same thing. They knew when the summer was in the past, so they could prepare the coffee plants for the next season. But nowadays, it's like a guessing game. And then this was really, really interesting. Someone mentioned that weather now comes in different combinations. So this coffee farmer said there was a change that now it rains, and when it rains, it gets hot. It used to not get hot. So in other words, it's not just that rain and temperature are changing kind of independently, but they come in different combinations. So this means that we need to look at the interactions between precipitation and temperature in our models. And then, obviously, everyone can see that bad weather reduces their harvests. So there's more unpredictability in how much return they're going to get. And then this poor harvest actually leads to debt, which means that if they had a bad weather year, it might take them a while to recover from that. And finally, migration is an alternative that a lot of people recognize. When the crop yields are not good, they mention that younger people decide to migrate because their livelihood depends on that. But migration is also not cheap, especially in recent years. And many people now, especially like in the MMP data, over 80% of the migrants are undocumented migrants. And many of them rely on smugglers. And smuggling fees have been on an upward trajectory, which means that the family needs to save money first in order to be able to finance this move. And if you actually had a poor harvest and debt from that, that actually stalls that opportunity for you. So this tells us that there might be heterogeneity by households, income or wealth status. So what if we put all of these insights together into our analysis and come up with a specification, simple specification that can be estimated? So here, our output is first US trip, and we're looking at precipitation in the previous year and temperature in the previous year. And we also look at the same kind of measures 2 years ago. So we don't make it more complex than that, going to 3-year or 4-year lags, because we're going to do all sorts of interactions across. So we want to keep the model simple and manageable. So we include all the exogenous indicators at the individual and household level. And we also introduce interaction, dummies for state times year. So basically, the first insight that we heard about that was meaningful for this modeling was combinations of precipitation and temperature matter. So we introduced interaction between precipitation and temperature at both lags. And we considered a full spectrum of weather events, so not just bad weather. So this is actually a bias in the literature. A lot of people want to control for disadvantaged, weather that's not favorable to your production. But good weather can also help you save and finance a migration move later. So we want to control for the full spectrum of good and bad weather. And again, like many studies, we compare each community to its own normal to take into account potential adaptation. So hot weather in a normally hot place doesn't mean anything, but hot weather in a cool place means something. And then we introduce interactions across time lags. For example, precipitation last year times precipitation 2 years ago, to consider sequences of events and also to take into account intensification of responses. In other words, let's say, good weather is followed by bad weather. Does it mean the same thing as 2 years of good weather in a row or something like that? So basically, we want to consider how these sequences matter. And then we test for heterogeneity by household wealth status, because migration is so costly. Yes.
Excuse me. So there's a clarification, borderline clarification question by one of our PhD students. Gudong is asking whether during the same period, has there been any technical improvement for agriculture throughout the period that you observe? So this may become a confounder to diminish the influence of weather.
Yeah, absolutely. So, that would be captured in a year fixed effect if it's same for the entire country, or state times year effect. So there are major changes, and I can talk more about this in the discussion section. So the biggest change is the change in trade. So basically, after 1994, because of NAFTA, cheap corn comes into Mexico, from the U.S. So that makes corn production really not very profitable. So there are these changes, and we're hoping they're captured by these fixed effects. But it's a really good question. We also thought about insurance schemes, because, if there's a weather insurance, then that could help. And we started collecting some administrative data on these insurance schemes. But then during the field work, farmers were really not very upbeat about this insurance. They felt like they were being frauded. They could never get the money back, so on and so forth. So I can kind of provide some insight into this, but, great question. So let's see, how am I doing on time? Okay, so I'm coming to the end of a few more slides and then I'll be done. So again, we use the Mexican migration project data, but we're kind of more careful in how we select the sample here. So we don't just throw in everything, all the communities here. So remember, the mechanism we have in mind here is rainfall affects, agricultural production, and through that, migration. So we basically exclude urban communities from our analysis here. This means that we are stuck with 97 rural communities and not 170 total communities. And we assume agriculture is the main mechanism. We don't use any data on agricultural yields here, but we actually do have administrative data at the municipality level for every year starting in 1980. But that data is very, very messy. So we spent a bunch of time, cleaning it. We're still not sure we're doing it right. So it's a future project. And in the end, this gives us information from about 56,000 individuals. These are nested in 13,000 households. So a similar data set, but kind of a reduced version of that. And then we focus on first migration trips between 1991 and 2018. So our weather data, this kind of fine resolution weather data, starts in 1980. And we reserve the period between 1980 and 1990 as the baseline. So we want to compare each community to its baseline in that period. And that's why our main analysis starts from the post-1990 period. And then all weather indicators are computed in terms of deviations from the mean in this normal baseline period. And we take the difference and we divide it by the standard deviation in that period. And again, we kind of consider the full spectrum, and we create 5 weather categories. So very wet and wet would be, good weather, and then normal would be normal, and dry and very dry are bad weather in terms of agricultural production, similar with heat. So what do we find? So here are the main takeaways. We find that combinations of rain and heat matter. So it's not just these kind of independent effects, but the effects really come through when combined. In other words, low rainfall does not mean much unless it's combined with hotter than average weather. So we really need to consider these things together. Second, we find very strong evidence that both good and bad weather matter. And we also find very strong results for heterogeneity by household wealth. Basically, rich households migrate when last year's weather is bad. In other words, they can respond immediately when there's a bad weather event. So here I'm just showing some coefficients estimated separately for wealthy and poor families. And here wealth is measured with the number of properties they own. And the survey data actually allows us to differentiate between properties that were bought with migrant remittances. So if there was a prior migrant in the household versus, properties bought with other income. So we're using that to differentiate. And here we see that very dry and hot weather, which would be terrible for production, creates this positive response from wealthy families, but no such result from the poor families. And then we see that poor households migrate when last year's weather is good. So basically when it's wet and very cool, that means poor households can send a migrant. So this is evidence for credit constraints to migration, and poor households need some savings in order to finance the move. And remember, we looked at the sequences of weather events, and we find these sequences to matter, but only for poor households. So basically, we find that poor households migrate especially at higher rates when weather is bad 2 years ago and good last year. So basically, you have a negative shock, and then you have a positive shock, you save money, you make up for the loss, and then you can send a migrant. So what does this all mean? We can see clearly that migration offers an adaptation strategy to weather. And most migration in this setting is temporary. So most of these migrants go and eventually return back. And we do estimate some models looking at the duration of stay, and we find that poor households on average stay longer than rich households, which actually confirms the credit constraints idea. And then we see that rich households can resort to this adaptation strategy a lot faster. They can respond immediately, whereas poor households need to experience kind of a good weather event first. And then from kind of a scholarly perspective, considering these combinations and sequencing of weather events, in addition to their full spectrum, both good and bad, is crucial on understanding weather and migration link. So here in this talk, I think we're presenting a biased view that, the second half of the talk or the simple kind of OLS, well thought out models perform better. But I think both the ML, the machine learning, and OLS have something to contribute to this question. We see here that when we have a well-specified parametric model, especially if we have like deep domain knowledge, then we can kind of recover insights into the mechanisms linking weather to migration. But then in the non-parametric models, we're actually able to see the predictive accuracy of this entire enterprise. Whether we include weather or not, we see that at the individual level, our predictions are still not that accurate. So this should make us question both our theories and the data that we collect. So I think they're kind of complementary, and I hope kind of you also receive it as such. And yeah, this is all I have for now, and I'm looking forward to hearing your thoughts and questions.
Thank you very much, Filiz, for a fantastic talk. This was super interesting. I wish that most of our master students have been there, because we have been teaching them 2 weeks ago use of machine learning and big data in comparison to the like standard models, like in social research generally. This is a great lecture for all of them to see field work, like standard models as well as machine learning covering all together. I wanna just ask the audience whether they have any questions. You can raise your hands and then unmute yourself to ask the questions directly to Filiz. There's one question that is posted already on the chat function by Emilio Dalra. And what is the level of aggregation to define weather event, month, week, and day? A clarification question.
Yeah, so here the results are on annual, but we spent a lot of time because we have daily and monthly data. So we've created some measures that are a result of that. For example, we measured the number of consecutive days of a weather event, and then aggregate from that. But I think the really interesting direction here, which we tried to go for a while and then realized just it would take a lot more time than we thought, is actually customized weather measures based on the crops that each municipality is producing, and then looking at what kind of weather events those crops are most sensitive to, and then basically creating measures on a monthly basis based on that sensitive period. But that turned out to be really difficult. And we have a lot of, agronomers on campus. So we've been talking to them, and apparently this is more of an art than science, knowing when a crop is more sensitive in a given context. So, some people suggested using alternative or additional measures like soil moisture or other things, but then it just suddenly got very complex and started going into a direction that I don't understand. And so, but that's kind of where we want to go in the future, because I think, I made a big point about kind of the resolution and how measuring things at the community level makes a big difference, but we're still aggregating things over year. And that's not what we want to capture. Maybe, for a crop, it only matters what happens between July and August. And we want to be able to capture that. So we did experiment with this, a simple distinction between the winter harvest and the summer harvest, and computed different measures for those periods. But that didn't go very far.
Well, thank you so much. Thomas, you have a question, I guess, so you can unmute yourself and ask the question.
Thanks, Berkay. Thanks, Filiz, for a great talk. I thought it was fascinating, and it's nice to, I'm also teaching on the course that Berkay is teaching, so we're teaching these type of methods, but rarely get in touch with the real research. So I'm asking my question about the research, but also to you as an expert in the field of doing big data and machine learning stuff. So, and it's just as a warning, it's kind of a bit of a, let's say it's a bit of a provocative question. And it is because I feel a bit like I understand the process that you're going through. You're doing first some predictive modeling, and then it doesn't work very well. And then you go on the ground and you find out about, like what might be the reasons. And then you come back to your data and you run some models, and now they work much better. And eventually it seems like a bit like, eating your cake and having it too, because, like first you do some predictive modeling and then you come up with some mechanisms as well. And so my question is, how is this different from data mining?
Yeah.
That you're kind of basically seeing your data and then it doesn't quite work. And then you're kind of adjusting your models and you're coming back and then it works better, but then you stop, right? That's the problem, that then at some point we stop, and because now our results are satisfying. So
I know.
Don't take it the wrong way. It's just, I would be interested in.
I know. I don't know. Like, I don't also kind of, I don't know the best kind of way to answer this question, but it is interesting, right? So on the one hand, I think one lesson that I take from machine learning, like that approach to everything else that we do, is I think the importance of out of sample prediction. And in most kind of estimations that we do nowadays, I'd like to set aside, especially when we're in a data rich position, like we are with the Mexican migration project, like some portion of the data, aside in order to see kind of the overall performance of your model. I think it's not okay to use the same sample to estimate your model and then kind of evaluate its kind of performance, right? So it's you're already giving yourself the upper hand. So I think that's kind of a general lesson that I take away. And I think one lesson that I learned from this kind of ML enterprise is kind of the limitations of our models. Again, kind of when you focus on this in sample fit and in sample R squares, whatever kind of performance measure you're using, you're kind of buying this overly optimistic picture about your models. And then when you don't do that, you see it's kind of more sobering. So I think, I'm right up with you there, but what's the alternative? So I think, this is kind of part of a bigger discussion in the social sciences, right? So it's like, should we register our hypotheses? Should we kind of tie our hands in a way that makes our results kind of more credible? And kind of, I'm totally on board with that. But then as a researcher, I know how kind of these little decisions you make along the way, it's hard to know where things are going to go. And it's hard to, I think it's easier to almost design an experiment where you want to test for one thing and say everything else will be controlled. So here's how my experiment is going to look. And here's my hypothesis. And I'm registering that. I'm looking for one thing. But I think in something as complex as the weather migration relationship, it's hard for me to specify all of these linkages. And what does it mean if it doesn't hold? Does it mean the hypothesis is wrong, or was I measuring some of these things in the not correct way? So I don't know what the solution is. I think we do need some exploration until we establish some really robust stylized facts. And then I think we can say, okay, now we're kind of moving into the confirmation phase where we want to be really, hard on ourselves in terms of not leaving anything to chance, and registering these hypotheses. For example, now that we know maybe these combinations matter, or particular sequences matter, in the next analysis, someone might be able to say, okay, so I want to confirm this, and I'm only going to test for this one result, and only going to look at that, not like all the other interactions. So I think that's kind of one solution I see out of it. Otherwise, kind of very rigid stances on registering hypotheses, I think sound great, but doesn't really match with the reality of how we do research. So, that's kind of my thing.
No, I agree. As researcher, you know that that's just not how it works. That like you go on to a data set and you have everything is clear before you've even seen the data. Just as a brief follow-up, if I may, because you said like one part of the solution is the out-of-sample prediction. So I was wondering when you have those three different samples, how are people allocated to those samples? Because wouldn't you assume that if it's just random, then wouldn't you assume that it shouldn't make a difference? I mean, that's kind of, like if it's random allocation to samples, and the samples are large enough, and you're drawing your samples randomly from the overall group, then I don't know, is it really a test?
Yeah, so, I gave this talk last week, was it at Bocconi? And this was a long conversation around like how to stratify those samples. So we did it by people. We said we have 140,000 individuals. We're going to randomly select half of it. And then the remaining half, we're going to divide into that. But then, somebody was saying you should do it by time because, these people are observed over different time periods. But how do you do it by time? So, this is kind of one of the sticky points about like as social scientists, we do care about the structure of the data. We just don't dump things on an algorithm and, let it kind of find a pattern. So at first, for example, when we were using the person year structure, there's no way for the model to know that it's the same individual over time, right? So in a typical regression setting, we can say, okay, there's a fixed effect for individual, or like here's, these are all in the same community. For the community, you can do it, but at the individual level, you can't really do it without the algorithm using that individual ID to perfectly predict migration or non-migration. So I think, I don't know the answer to that, but basically we're experimenting these different things, and I think randomly selecting individuals seemed like the best strategy here.
All right, thank you.
So thank you, Filiz. We have another question from Diwakar, another PhD student of ours, and he's asking whether, just to clarify your answer, just given to Thomas, I believe, did your response mean that it's okay to do data mining with unexplored area, impact of climate on migration? Because one would assume that even with unexplored areas, researcher would have some hypothesis. That's what he wants to clarify, whether that is what you mean.
Yeah, so it doesn't have to be specific to the context. I think if your hypothesis is something as general as, combination of weather events should matter, and here's how I'm going to measure combinations and I expect, these combinations work in these ways. So I think you can use the hypotheses in one setting, in a different setting. But, I think, part of the big question is like, how do you measure these things? And that's where the big decision is done. And, you have no idea what the best way to measure that is. So I think we do need some exploration in that to kind of figure out, okay, so do we measure it in terms of standard deviations? Do we measure it on a continuous scale? For why do we do that? And first we need to kind of look at that. And maybe kind of the fit in the data is not the way to select this. Maybe kind of my hope was some kind of agricultural specialist would tell me, this is how you should measure it because X, Y, and Z. This is what we were looking for, like some expert telling us how to measure these things, but we didn't get the answer we were looking for. People were like, oh, we don't know. So then we thought, okay, so then we need to kind of play around with a few things to figure it out.
Perfect. Thank you. Evelina, do you have a question that you may unmute yourself and ask directly?
Thank you, Berkay, and thank you, Filiz, for the great presentation. It's inspiring. I have a question about the importance of migration networks. So especially in U.S. On migration from Mexico to the U.S., there's a lot of research that networks are quite important, especially and I can imagine for first time migration, it might be even more, because they can reduce the cost of migration, both monetarily, but also emotional, non-monetary cost, like, you are going into a community. And some communities in Mexico in general would have a more migration prevalence compared to others, like, as you said, with these cornfield communities, both past and present. So I was wondering whether you control in any way for the importance of networks that already exist in these communities, whether these would be included in the year in state interaction or any other way. Thanks.
Yeah, no, a great question, Evelina. So, in the first model, yes, like everything is included. Migration prevalence is measured as the share of people who've ever migrated in your community. And there's quite a bit of variation. So in some communities, 60% of the adults have migrated at least once, which is huge. In other communities, it's much lower, like 5%. And obviously this really matters. So in the second model, we kind of left them out initially because one of the things that we saw was, or we thought was, part of the reason for the mixed results in the literature is because they control for all these endogenous indicators, right? So you control for things that are a result of past migration patterns, like, how well off your community is, or how much migration out of your community do you observe. So we wanted to see the total effect of weather without kind of, including these kind of, immediating factors, like factors through which weather might have an impact. And that seemed to make a big difference. So we estimated these models with and without those endogenous indicators, and results are a lot less stable when we include these kinds of measures. And once we excluded them, then things became really robust to different measures that we use, like how we measure precipitation, how we measure temperature. So like that's one of the lessons that we want to basically highlight. But that being said, we want to understand how these things matter, right? So then we estimated our models separately for different types of communities. So communities with high migration prevalence versus low migration prevalence. And you're right, the response is a lot quicker and more possible for poor households in communities where there are established migration networks. So that really matters. But again, if we control for that, I think that takes away some of the weather effects. And, it's fine if your goal is not to identify how weather works, but if you just want to control for that. But I think if you really want to carefully model this, then you need to leave out certain things that are changed by weather, past weather.
So we do have Gudong and Emilio. So can I just get that order? Gudong, can you unmute yourself and ask your question, please?
Yeah. So I'm so excited that you can come here and give us such a wonderful topic, because I actually is one of the readers for your article that published in the ARS, and it's really your paper that drives me to become so interested in machine learning for social science. And so I actually have several questions, but most of them is just not to try to argue, but try to asking for your help. And so the first question is, for the causality identification, I think the impact from weather should be largely correlated or mediated by the income change, for instance, income decline or income increase, because it will be mediated by agriculture. So if you also input the income status of a household, then would that become a collider for us to identify the pure weather's impact? Yeah. Have you ever?
Yeah, absolutely. So if your goal is kind of causal identification, you shouldn't even include those, right?
Yeah.
And you should even like think about including something like education, because if your family has resources, those resources are weather related, then, so we've done like pure weather indicators, like with nothing but just weather, and these results hold. But from a policy perspective, you want to be able to say something about, poor and rich families, kind of their response, their ability to respond. So it depends on kind of what audience you're addressing. But one of the points that we want to make is that if you want to address this issue, some families, because of their resources, whatever they're caused by, will be able to respond a lot quicker than other families. And we tried we didn't include income precisely because of the reasons that you're describing, because income is very much related to kind of immediately what happened to you in the last year or 2 years ago. But we also didn't include land for that reason. And, property seemed like, especially those both without, remittance income, obviously, weather would matter with that, but like number of rooms you have in your house, like it's not directly related to agriculture. So anyway, like we try to find this happy medium between writing about things that we want to, like giving a message that we want to give that is meaningful, but also like coming up with a pure specification. So basically, if we exclude everything and just have weather, we still have this kind of pattern. Obviously not the heterogeneity angle, but then the other combination sequencing, all of that holds.
I see. And so another question is, one of the main concern may be the so-called the cause of dimension. So as you also include maybe daily weather change and all those huge data sets, would that be something like some days or some kind of indicators may just correlated with the outcome just by some random reasons rather than by some real associations, just like people always try to pick up some related genes with other diseases, but many of those genes then we found that just doesn't work. It's just like there are too many dimensions, and so that there will be some fake correlations.
Absolutely. Absolutely.
So how do you deal with that?
All kind of variables you throw out there, and this is related to kind of Tomas's point right earlier, that the more things you try, the more likely you are to bump into something that is significant. And so yes, so maybe kind of out of sample testing of the model is kind of one answer to that. And also, I increasingly think that even with kind of machine learning, which supposedly shines when there are too many things that it can select from, I increasingly think that even there, we need to bring things that reflect our domain knowledge, things that should matter based on our knowledge of the setting, and maybe kind of give it to the algorithm at finer granularity, like we're here doing annual, maybe doing it monthly, because it can handle that, but not just throw in anything and let the model kind of come up with something meaningful. I think even there, domain knowledge should be meaningful and should guide the selection of things that we are feeding the algorithm. So our actually next step is, other than increasing the things we're giving the algorithm, we'll just try to reduce them and see if that helps a little bit. So yeah.
Yeah, so that's so helpful. And my final question is, as you said, I also got the same problem.
Do you mind we get to the last question to Emilio? And then if you have follow-up questions, I will stop recording. And then some of the PhD students will hang out for 10 more minutes to follow up questions. And then after the recording, that you can actually ask more questions to Filiz, who graciously agreed to stay a bit more. So can I just get Emilio your question, please?
Yes, thank you. I will just jump in. So I feel a little bit bad. I don't want to mute Gudon because I'm actually not a PhD student from LSE, but I'm an infiltrating guy from University of Zurich. But I guess one of the opportunities, I was invited to this seminar, so one of the great things, I've been trying to follow you around, and I feel it's in Australia. You gave talks, and then apparently my university doesn't give this opportunity, so I'll just go straight to the point. my question. So it's regarding the mechanism. So I found, your work really super interesting. And I think towards the end, you were going towards the idea of the mechanism, or try to open the box a little bit, which is what machine learning doesn't really allow you to do. So that's why you, and so I didn't really get, but I'd like to know from you if what you have in mind, also based on the film evidence that you gathered. It's regarding sort of the conceptual framework of a negative event, how this can impact migration. Because I have two stories in mind. I always have, and I still cannot find a solution. Maybe you have. So one is that when a negative effect, negative weather event, let's call it this way, impacts, this decreases the opportunity cost of migrating, because now USA, let's put it this way, becomes more attractive. But at the same time, and so you would expect an increase in migration. But at the same time, there is also, as we know in these areas, these are mostly liquidity constraints. And as you mentioned, this is a very costly type of migration. It's international migration. So at the same time, negative events can reduce your wealth and increases your liquidity constraints. So this will decrease migration. So these two effects really go the opposite directions. And I didn't get in your presentation if you can discern these two effects, or if anything, if you have also an idea, not maybe empirical, but if you got an intuition of it. Thanks.
Yeah, no, thanks so much. I don't know, right? So it's kind of hard to differentiate at this kind of deep level of what is driving this. So our interpretation obviously is kind of related to liquidity constraints because of this particular sequencing. So one thing that we hoped would help us, but didn't, was looking at internal migration as an alternative, because internal migration is, again, kind of addressing whatever problem you have at home, but it's not costly. And a lot of the work that is related to weather and migration actually highlights that internal migration is a more natural response to weather changes than international migration because of the costs and so on and so forth. But when we did this kind of specific modeling in the internal migration, the results were all over the place, right? It was kind of really idiosyncratic, and it was almost like, internal migration can be a response to anything. It's so easy that it's like you're not really picking up on this kind of weather signal there, which came as a surprise because the literature on Mexican migration would lead us to believe that, internal migration is a more natural response. So I don't know like how you would, the problem also, Emilio, is that to test for these kind of particular mechanisms, maybe you need to go deeper into kind of individual and household level measures that could capture some of these patterns, like their involvement in agriculture, their different kind of economic activities, their household structure. But then, like Gudong was saying, then you're like, okay, so then it's becoming all a little kind of complicated, the relationships you're positing. And so I think that's kind of a problem. One of the longer term projects or longer term ideas is maybe related to this. I want to see, and this was actually the reason for doing qualitative work in the first place. I want to see if people treat changes in the weather or respond to changes in the weather the same way they respond to some economic crisis, right? Like, let's say there's kind of sudden unemployment in your region and you have to migrate, versus you see this weather changing. So your entire community changing over time. Like, how do you respond to these different things? I don't have an answer for that, but I think we need kind of a more psychological model of how people are perceiving risks when it comes to these things and how they're perceiving opportunities in other places. And someone pointed out that a lot of the, disaster-related migration focuses on permanent migration. Like in Bangladesh, things are like water levels are rising, so you have to permanently leave. But this is the case we're studying is interesting because migration is temporary. So like the reason we're looking at duration of stay is maybe kind of trying to get at the motivations for this. Like, what does it mean to stay long versus short? What does it mean once you leave, if the weather continues to be bad, do you return or do you stay? So we're trying to also kind of look into that to maybe start getting into the questions you're asking. But the short answer is like, I don't know. I'm not able to differentiate between these alternatives.
So thank you very much for Great talk and great questions. And thanks also for answering my burning question, which was about internal migration. So I'm not going to ask anymore. So I just want to say thank you all on behalf of everyone.
Thanks
for
so
giving
much.
We'll stay, I'll stop recording now. We'll stay here for whomever wants to chat for another 10 minutes with Filiz for further questions.